So this will be the third part of our lecture 0, which is a review of the differential form of the fluid equations for you to prepare yourself with the derivation and understand the physical meaning of the continuity equation and the momentum equation. In the first part, we presented a pencast of the continuity equation. In the second part, we presented a pencast for the momentum equation. And in the momentum equation, you saw that we had too many unknowns because we have the three components of velocity, the density, and also all of the different stress terms. And so the vector momentum equation corresponds to 3 scalar equations and plus the continuity equation that gives us 4 equations. So we need to somehow reduce the number of unknowns. And to do this, we need relationships between the stresses and velocities. Basically, what we need is constitutive relations, is what we call them, constitutive relations. So we need stress. We relate the stress with derivatives of velocity, and so these are called the stress deformation relationships. So from this point on, to derive the Navier-Stokes equations in this third part of the review, we're going to derive the Navier-Stokes equations, which assumes that the fluids are Newtonian. The Newtonian fluids are those in which the stresses are linearly proportional to the strain rates, to the velocity derivatives. And so for this case, where we have linear relationship between rates of deformation and stress, we can write, so let's write this down, that we're going to limit ourselves to Newtonian fluids, where we have a linear relationship between stresses and the rates of deformation. So the general result for compressible flow is rather difficult, and so we're not going to include that here. Instead, we're going to assume that the densities are constant. We're also going to assume that we have isothermal flows, that they are not really important. The temperature changes are not really important, or there are no changes in temperature. And so that we don't need to consider at this point an energy equation. So we'll have fluid properties, the viscosity and the density, which are constant. So with these assumptions, it has been shown that the viscous stresses are linear with the strain, and for the case of the normal stresses, we can write the following. We have sigma xx, which is equal to minus the pressure, the thermodynamic pressure, plus 2 mu, where mu is the coefficient of viscosity of a Newtonian fluid, times du dx. We have sigma yy is equal similarly to minus p plus 2 mu times dv dy in this case, and sigma zz, the third normal stress, is equal again to minus p plus 2 mu dw dz. So note now that if we add the 3 components of the normal stresses, so if we write sigma xx plus sigma yy plus sigma zz, we are going to get, well, we're going to get the pressure, minus the pressure 3 times, and we're also going to get 2 mu times du dx plus dv dy plus dw dz from the terms that appear here that I've just written up here for the stresses. And so in an incompressible flow, we have that du dx plus dv dy plus dw dz is going to be equal to 0 because, right, incompressibility results in the gradient of the velocity equal to 0. So that means the sum of the 3 components of the normal stresses is going to be equal to, well, minus 3p, so I'll write 1/3 here equals to minus p. That is because of incompressibility. So now the shearing stresses can also be written as linear relations with respect to the rates of deformation, but we also have, in addition, symmetry, so that we can write that tau xy is equal to tau yx, and that is equal to mu times du dy plus dv dx. We also have that tau yz is equal to tau zy and is equal to mu times dv dz plus dw dy. And finally we have third equation for the shearing stresses, tau zx is equal to tau xz and is equal to mu times dw dx plus du dz. So here we have our 3 shearing stresses. So now we have all of the stresses as a function of velocity derivative. So we can put these stresses back in the momentum equation in differential form, and we are going to have now everything in terms of velocity. But notice that the stresses appear in the momentum equation already in derivatives, and so that means that when we put these back in the equation, the velocities will appear in second derivatives now. So for example, if we consider this first term involving sigma xx in the momentum equation, you will, when you put in ddx of sigma xx, you're going to have a first order derivative of the pressure and a second order derivative of the velocity. We assume that viscosity is constant. So now if we look at the stress terms of the momentum equation, so let's consider the stress terms, and let's look at the first equation, the x direction of the momentum equation. And those terms were, well, we had ddx of sigma xx plus ddy of tau yx plus we had ddz of tau zx. These were our stress terms, and then in addition we had in the equation the body force term and the acceleration terms, which I've omitted here for the time being. So these terms now I want to write with respect to the velocity derivatives. So this same thing can be written as, well, the first one, sigma xx is minus p plus 2 mu du dx. So that's d dx of p minus p and plus 2 mu, and I get the second order derivative of u with respect to x. Now if I look at now the second term here, the second stress term, d dy of tau yx, then I am going to get, well, I have mu multiplied by, I'm going to get now second order derivatives, and it's going to be the second order derivative of u with respect to y, and a mixed derivative involving y. So second order derivative of v with respect to y and x. So that's the second stress term, and the third stress term also all multiplies by mu, and we're going to have second order derivative of w with respect to z and x, and plus second order derivative of u with respect to z twice. So those are our stress terms now, but now all expressed in terms of the velocity, the rates of deformation, the velocity derivatives. So now we can rearrange these terms, the terms involving second derivatives, and I'm going to take one of these. Notice I have a 2 here in front of it, but I'm going to take just one of it, and I'm going to take this term over here and this term over here and put them all together. So I'm going to rewrite this as minus dp dx, that remains the same, and plus mu times second order derivative of u with respect to x plus second order derivative of u with respect to y plus second order derivative of u with respect to z. And the other terms that I was left with are the other terms here. 2 of them involved mixed derivatives, but I also have one term left from the one that previously had 2 mu, so that's the second order derivative of u with respect to x, and the terms with mixed derivatives, which are second order derivative of v with respect to y and x, and second order derivative of w with respect to z and x. So notice here that for this term, for this whole term, I can rewrite it in this way: mu times d dx of du dx plus dv dy plus dw dz. Now, with incompressibility, this is equal to 0, because of incompressibility. Which means that we're only left with the gradient of the pressure and this term involving second order derivatives of the first coordinate of velocity. So now we can write the x direction equation of the momentum equation as, well, we had for the whole equation, we had on the left hand side we had the acceleration terms. Let's write the acceleration terms here. On the left, it's rho times, so it's the first component, so it's du dt, the first component of velocity, the unsteady term plus the convective terms involving the first component of velocity, which is our du dx plus v du dy plus w du dz, and that is equal to our gravitational force. Let's write rho g in the x direction, and sorry, this is a minus sign here, minus dp dx, the normal surface force, and the tangential surface forces, which are mu, we just derived that, times the second order derivatives. I have a little space here, let me see, second order du dx plus second order du dy plus second order du dz. So similarly, we could write the two other equations, the y direction and the z direction, but that would be a little long to write, a little cumbersome. So instead, we're going to use vector notation. So you see that on the left-hand side, we're going to have rho, and we're going to have the unsteady term is going to involve du dt, dv dt, and dw dt, so that's going to be d dt of the whole velocity vector. And then we're going to have the convective acceleration term, which involves v dot nabla times v. And on the right-hand side, we're going to have rho times g as a vector, the gravity as acceleration of gravity as a vector now. And we have minus, well, dp dx, dp dy, and dp dc. So it's the gradient of the pressure. And plus mu, and we're going to have the second order derivatives of each component of velocity, which is the Laplacian second order differential operator applied to the velocity. So this is our vector form of the Navier-Stokes equations involving a Newtonian fluid with the assumptions of incompressibility, rho equals constant, so incompressible Navier-Stokes. We've also assumed isothermal conditions, and we've assumed that the viscosity is also a constant. Here we have written this second order differential operator, which is the same as ddx second order plus ddy second order plus ddz second order. So we see that these are three equations. It is one vector equation equal to three scalar equations plus continuity. We have, therefore, four equations, and our unknowns are the three components of velocity, also the pressure, and the density. So we have five unknowns. So to close the system, to complete the system, we need an equation of state. With an equation of state relating the pressure and the density, then we have a complete system. But notice that this is a nonlinear second order PDE. So it is quite a complex system of equations, and in fact there are very few known solutions to this equation. Very, very few equations. Usually the very few equations involve some particular sort of symmetry where the nonlinear term disappears, for example. The nonlinear term is, of course, this term involving the convective derivative. This term here is our nonlinear term, which produces most of the problems, and when there are symmetries we can perhaps cancel out, eliminate that problem, and then get an analytical solution, but in general there are no analytical solutions, and the only general approach is the computational. Which is our business here at hand. So here you have, we have derived the Navier-Stokes equations based on some physical understandings, physical discussions involving the stresses, Newton's law, and the assumptions of Newtonian fluids.